In part 1 of our lesson on the ambiguous case of law of sines, we will investigate when does the ambiguous case happen. Let's take a look at this diagram here, and we are going to make triangle ABC. So we're given some constraints here. Point A of our triangle has to be here at the origin. Point B is going to be at this point 5, 12. Now point C of the triangle is going to be somewhere on the positive x-axis. So it can't be over here on the negative x-axis. Point C will be somewhere along the positive x-axis. We don't know where it is right now. Angle A is known, and what that means is the angle between the positive x-axis, where point C will live, and this side here is fixed, so that angle cannot change. Using the distance formula, we can find side C, because remember, point C is somewhere along this x-axis here, so wherever point C is, that would be angle C then, wherever it is. So the side opposite of angle C is going to be lowercase c. And we can find the length of side C by using the distance formula. So we know it would be the square root of the x value here, which is 5, minus the x value here, which is 0 squared, plus the y value here, which is 12, minus the y value here, which is 0 squared, and we get that c is equal to the square root of 5 squared plus 12 squared, which is the square root of 25 plus 144, which is radical 169, which is 13. So let's label that on our diagram. We know that the length of side C is fixed. It will be always a constant of 13. The next thing we're going to do is look at 4 different cases of what could happen with the length of side A, and we know that side A will be the side of the triangle that is opposite from angle A. So side A will be the side that connects point B to point C somewhere along the positive x-axis. Now, one thing that we should consider before we explore those 4 cases is, let's think about the height that point B is above this positive x-axis. If we were to drop this perpendicular line here, we know then that the length of this dotted segment is just going to be the y value of the point. So we know that this is 12, and we're going to use that to help us look at these 4 cases. In this first case, side A is less than 12. So what that means is side A won't be long enough to reach all the way down to that x-axis. So whatever the length of side A is, we know that it falls short of reaching the x-axis because we know that the height of point B is 12. So if side A is less than 12, then that means it's not long enough to reach all the way down to the positive x-axis. And when that happens, no triangle can be formed. Next, we'll look at the case where A is exactly equal to 12. So if A is exactly 12 units, then that means A was exactly just long enough to reach down here to the positive x-axis, and that means this would be point C. So then what happens is one triangle is formed, and it is a right triangle. So one right triangle is formed. Next, let's look at the case where A is greater than 13. So that means side A will have to be longer than this side, which is 13. So if we put that in our picture, and then we rotate it so that the end point of side A lands on the positive x-axis, we can see that we are going to get a triangle. One triangle is going to form, because remember, the end point of side A cannot land over here on the negative x-axis. It must land over here on the positive x-axis. So we end up getting a triangle formed. Then that means that point C is here, and one triangle is formed. In the last case, we are going to look at what happens when A is in between 12 and 13. So what that means is it's longer than this perpendicular distance, but it's shorter than the 13. So when that happens, think of it like a hinge. The side will swing until the end point of the side hits the positive x-axis, which could happen here. And if we let it keep swinging over to the right, we see that it will also hit the positive x-axis here. So there are two different values for C that are possible. So we'll call this C1 and this is C2. So we could get this triangle being formed, or we could get this triangle being formed. So you have the smaller triangle, which has that obtuse angle in it, or you have this bigger triangle, which is all acute angles in it. So in this case, there are two triangles formed. Now this is what we mean by the ambiguous case, because you don't know if it's going to end up that no triangle gets formed, or maybe a right triangle gets formed, or another type of triangle, you get one triangle, or maybe two triangles get formed. From the beginning, we only knew one angle in the triangle. Remember, we knew angle A, so angle A is the same in all four of these cases. Side C is the same in all four of these cases. What we didn't know was the length of side A. And so when you have only one known angle in a triangle, that's called the ambiguous case. So we're ready now to look at an example and explore this in more detail next. So here we are being asked to solve triangle ABC. So let's go ahead and start getting a picture going here. And we can label the vertices A, B, C. We are given that angle A is 55 degrees, side A is 9 centimeters, and side C is 10 centimeters. So as we assess our diagram here, we see we have an angle and its opposite side, and then we have another side whose angle we don't know. So this is the perfect case to use the law of sines. The sine of C divided by its opposite side, which is 10, has to equal the sine of 55 degrees divided by its opposite side, which is 9. Solving for the sine of C, we get sine of C is equal to 10 times the sine of 55 degrees divided by 9. So the sine of C is going to equal, we have to pick up our calculators, and we will take 10 times the sine of 55, close your parentheses, divided by 9, hit enter, and we see that we get 0.9101689, whole bunch of decimal places. Now let's think about this for a moment. This is a positive number, and when the sine of an angle is positive, we know that that angle could live in quadrant 1 or 2. Now let's use our calculators to find out what this angle is. So on the left-hand side, of course, we will take the sine inverse of the sine of C on the right-hand side. We will have to do the same thing. So we know we are taking the sine inverse of this number, 0.9101689. Now my suggestion is you'll want to store that number in a memory location, so let's go ahead and store that in A. Make our next calculation a little bit easier. On the left-hand side, we will get C, and on the right-hand side, we know we have to do second sine inverse memory variable A. Close your parenthesis, hit enter, and rounding to the 10th place, we see that we are going to get 65.5 degrees. Now remember what we just talked about a minute ago though. We know if the sine of an angle is positive, which is what we had here with the 0.9101, etc., we know that means that that angle could be in quadrant 1 or it could be in quadrant 2. So the 65.5 degrees is here in quadrant 1, and that tells us our reference angle. Then to find the quadrant 2 angle, just grab your calculator and do 180 degrees minus 65.5 degrees, and we find out that the quadrant 2 angle is 114.5 degrees. So in this case, we are getting two possible angles for C, and the reason that happened is because we have the ambiguous case where only one angle in the triangle was known. So when you're using law of sines, with only one known angle, you will get the ambiguous case, and you will have to check for 2, 1, or 0 triangles. In this case, we're getting 2 possible answers for C, so that means we are going to have to draw a second triangle. So now it looks like this first triangle we're going to call triangle 1. So let's give everybody a subscript over here of 1. In the second triangle, we'll call it A2, B2, and C2. We know that angle A is still the given angle, 55. We know that side A is still 9, and side C is still 10. Those are the givens, and those cannot change. What does happen is that angle C has 2 different possible values. So let's put the 65.5 degrees here and the 114.5 degrees here. And you'll notice I'm not bothering to draw my triangles to scale. I'm not trying to make this look like an obtuse angle. The triangles that you draw when you're solving these problems are just a place to hold the givens and your answers as you work through the problem. So now we need to solve 2 triangles, and let's do them separately. We'll go ahead and finish the first triangle. Now we can find angle B really easily by using the triangle sum theorem. So we know that B1 is going to equal 180 degrees minus the sum of the other 2 angles, which is 55 degrees plus 65.5 degrees. Enter that in your calculator. And we find out that B1 is equal to 59.5 degrees. Let's get that in our picture. Finally, we can solve for side B1 over here. So we get that B1 divided by the sine of its opposite angle, which would be 59.5, is going to have to equal, let's use the givens, we've got 9 divided by the sine of its opposite angle, which is 55 degrees. We'll cross multiply this sine of 59.5 up to the right-hand side, and we get that B1 is equal to 9 times the sine of 59.5 degrees divided by the sine of 55 degrees. So let's enter that in our calculators. We've got 9 times the sine of 59.5, close your parenthesis, divided by the sine of 55, close your parenthesis, hit enter. And rounding to the 10th place, we find out that B1 is 9.5. And the units of B1 are going to be the same as the units of the other sides, centimeters. So in our work, we should box in all our answers. We knew B1 was 59.5. And way back over here, we found the 2 angles for C. We want to make sure we box that in. So just a reminder, show your work, box in your answer, show the work, box in the answer, show the work, box in the answer. Now we can get B1 on our picture here. So we put the 9.5 right here. So this triangle now has been solved. Now it's time to turn our attention to the second triangle. And to find angle B, we'll use the triangle sum theorem. So B2 is going to equal 180 degrees minus the sum of the other two angles, which is 55 degrees plus 114.5 degrees. We enter that on our calculators. And we discover that B2 is equal to 10.5 degrees. Let's get that in our picture. Now we'll be able to solve for side B2 because we have its opposite angle. So let's set up that proportion. We get B2 divided by the sine of 10.5 degrees is going to have to equal our givens of 9 divided by the sine of 55 degrees. We will need to cross multiply the sine of 10.5 up to the top. So we get B2 is equal to 9 times the sine of 10.5 degrees divided by the sine of 55 degrees. So let's enter that in our calculators. We get 9 times the sine of 10.5, close your parenthesis, divided by the sine of 55, close parenthesis, hit enter. And rounding to the tenths place, we see that B2 is going to equal 2.0, and the units will be centimeters. Let's be sure to box in our answers in our work. And now we can get B2 on our diagram, 2.0. And now we have solved the second triangle. So just to recap here, we ended up getting two different triangles that could happen, and whenever you're using law of sines with only one known angle, and that was the case we had, remember in our givens we only had one known angle, we know now that is the ambiguous case. So we have to check for 2, 1, or 0 triangles. And as we continue on in the next lesson, we will explore what happens in all three of those cases.